Welcome, computer science students. Are you currently staring at your algorithmic analysis textbook and feeling that rising wave of math anxiety? Well, you are in exactly the right place. Today, in this explainer, we're building your ultimate study guide. We are going to completely strip away all that intimidating notation and use plain English to totally demystify hash tables, collision resolution, and exactly how we actually measure their performance. By the end of this, the math won't just make sense, it's going to seem pretty elegant. So here's our roadmap for today. First, the direct address problem. Second, enter the hash table. Third, resolving collisions with chaining. Fourth, understanding the load factor. And finally, unsuccessful versus successful searches. Let's get right into it.
Okay, let's dive into this with section 1, the direct address problem.
I want you to imagine a massive, an unimaginably huge warehouse, right? And in this warehouse, we permanently reserve a shelf for absolutely every single item that could possibly exist in the universe. That is our universe of keys, denoted by a capital U. It's literally enormous. But the actual keys that we really use, they make up just a microscopic fraction of that universe. When we talk about finding items in computer memory, direct addressing is basically this very simplistic but wildly wasteful method where we assign a permanent, reserved spot for absolutely everything. Now, because every possible key has its own dedicated spot, a direct address table makes operations incredibly fast. You want to search for key K? Boom, just go straight to slot T of K. Want to insert? Drop it in T of X.key. Delete? Just wipe that spot to nil. It takes a constant, tiny amount of time. But remember that massive warehouse? The sheer space required to build a physical shelf for the entire universe U? Yeah, that makes this approach completely impractical for real-world programming. We need a smarter solution. Which brings us to section 2, enter the hash table. So to build a much smarter, smaller, and highly efficient warehouse, we need a system to figure out exactly where things go on the fly. Enter our brilliant indexing clerk, the hash function, which we call H. This function takes any key from that massive universe U, does some quick math, and instantly maps it directly to a specific slot in our smaller table, somewhere between 0 and m-1. Instead of reserving space for everything in existence, we just compute exactly which shelf an item should sit on the very moment it arrives. So, the crucial point is, well, what happens when things get crowded? Section 3, resolving collisions with chaining. Okay, what happens when our brilliant indexing clerk makes a mistake? Or actually, scratch that. It's not a mistake. What happens when the clerk assigns two totally different items to the exact same shelf? Because our new table is way smaller than the universe of keys, this isn't just possible, it's pretty much inevitable. We call this a collision. Let's look at a specific example right from the source material. We've got an actual key, K2, and another one, K5. Our hash function runs, and oops, each of K2 equals each of K5. They're pointing to the exact same index in our array. They both want the exact same spot. We obviously can't just overwrite the data, so how do we handle this? Well, we solve this using a beautifully simple technique called chaining. When a collision happens, we absolutely don't panic. Instead, we just build a linked list extending straight out from that specific shelf. So the step-by-step tutorial looks like this. First, you compute the hash index for your key. Second, you go to that specific slot in the table. And third, if there is already an item sitting there, you just simply link the new item to the very front of the existing items. It's literally like a chain. This does change our basic operations just a little bit, but they stay highly efficient. When we insert, we compute the hash and drop the new item right at the head of the linked list. And the source data strictly points out, new insertions always go straight to the front. To search, we just jump to the hashed index and scan down that specific list until we find our key. And to delete, we find it in the list and just pluck it out. Simple, right? Let's move to section 4, understanding the load factor. Now that we've got our smart warehouse running with chaining, we really need to know how well it performs. Are those linked lists going to get way too long and slow us down? To answer that, we have to look at the mathematical performance analysis, starting with absolutely our most important metric. This is the load factor, represented by the Greek letter alpha. The formula is literally just n divided by m. Please don't let the notation scare you. N is just the total number of actual items we have stored, and m is the total number of slots in our hash table. In plain English, the load factor alpha is simply the average number of items sitting in each slot. So if we have 100 items and 10 slots, our alpha is 10. We average 10 items per list. To actually make our performance math work, we rely on a really important assumption called simple uniform hashing. This just means we assume our indexing clerk, our hash function, is fair. It absolutely does not play favorites. Any given key has an equal probability, specifically 1 over m, of landing in any of the available slots. It distributes the items evenly, so we don't just end up with one massive, endless linked list, while the rest of the entire table just sits completely empty.
Let's move to and see how this builds in Section 5, unsuccessful versus successful searches. Let's see how all of this actually builds into our final expected search times. There are basically two scenarios when you're searching for an item. Either the item isn't there, that's an unsuccessful search, or the item is there, which is a successful search. Let's start with the unsuccessful one. You look for an item, and it's missing. How long does that actually take? Well, you compute the hash, right? That takes constant time, or 1. Then you go to the slot. And because the item isn't there, you literally have to check every single item in that linked list just to be absolutely sure it's gone. How long is the list? Well, on average, it's our load factor, alpha. So the expected time is big theta of 1 plus alpha. 1 step for the hash, plus alpha steps to search the chain. Makes perfect sense.
Okay, now for the successful search. If you look at the source text, it hits you with this super intimidating string of expected value summations, right? It ends in 1 plus n minus 1 over 2m, which equals 1 plus alpha over 2 minus alpha over 2m. Look, I know this looks like an absolute nightmare of variables, but take a deep breath because we are going to translate this directly into plain English right now. This brilliantly illustrates why algorithmic analysis is honestly so cool. All that complex, scary math is really just a highly precise way of proving a basic logical truth. If the item actually is in the list, you obviously won't have to search the whole list to find it. On average, you're going to find it about halfway through. So instead of searching alpha items, you only search alpha divided by 2 items. But remember, in big theta notation, we drop the constants. So whether you search the full list or just half the list, the overall time complexity simplifies to exactly the same thing, theta of 1 plus alpha.
So let's bring the whole shebang together and compare our two strategies. The direct address table, it required an impossibly huge universe of space just to give us a search time of theta 1. But our hash table with chaining totally fixes that space problem. It only uses space proportional to our actual keys. The trade-off? Well, our search time becomes theta of 1 plus alpha. We sacrifice just a tiny bit of speed to save an absolute mountain of memory space. It is a massive win.
To wrap up this study guide explainer, I really want to leave you with a quick question to test your new intuition. We know the search time is 1 plus alpha, right? But what actually happens if you just keep adding items to your hash table without ever increasing the number of slots? What happens to your program's performance when that load factor, alpha, grows infinitely large? Think about the length of those linked lists. Keep that in mind for your next exam, and hey, happy studying!